Alright, thank you all. So my talk is going to be on detecting gravitational waves with LIGO. So before I came out to Penn State, I actually had worked at the LIGO Hanford Observatory, and this was last winter when I came back to visit some friends. And so this is an image of what the control room looks like in LIGO. This is in the Hanford, Washington site. There's another site in Livingston, Louisiana. They look almost exactly the same, except that ours is of course better. But they've got these gigantic screens which are just plastered all across the walls, kind of like this, and that's just to basically like a diagnostic check on the detector to see what is going on. And it's hard to make out, but you can see this curve right here. There's a red curve, and it's up a little bit above this other grayed out curve below it. And so what's actually going on, they were having some glitches at the time, and so their performance wasn't as good as it could be. It's up here, and the curve should be down there. So even though LIGO has made international headlines, it's still very much a day-to-day process of trying to get the detector into a good state where they can find more gravitational waves. So let's start off with, what is a gravitational wave? Well, these were predicted from general relativity, who Einstein, of course, was famous for writing this. And it was first published in 1915, and actually 100 years after GR was published, the first gravitational wave was detected. And in 1916, Einstein first predicted gravitational waves. And 100 years after 1916, the first paper was published on the gravitational waves. So that's a really nice coincidence there. And now, Einstein originally had thought that this would be completely undetectable. This was really just a theoretical curiosity. And so a lot of newspapers came out with a headline that, Einstein is proven right once again. Well, we actually kind of proved him wrong in a sense, but the theory was still good. So what is a gravitational wave? So if we imagine that a gravitational wave is coming into the screen, a gravitational wave is going to stretch and shrink this screen. So it does this in two axes here. They're both 90 degrees to each other. So if we have a ring that's just sitting in this screen, it's going to get stretched and squished. And so the frequency, how often it does this, is kind of the characteristic parameter of a gravitational wave that LIGO detects. So the faster that it oscillates, the higher the frequency. So LIGO is detecting gravitational waves at around 200 hertz. So waves that are stretching and shrinking the screen 200 times a second. And if you are going to imagine that maybe we've got a gravitational wave that's going through the Earth, this is a scale of effect vastly exaggerated. So again, these are very, very small effects. But if you have gravitational waves that are passing through the Earth, you can see that the Earth is actually getting stretched and squished on a very much larger scale than is actually happening, of course. So that's what LIGO is trying to detect. And more specifically, what they're trying to detect is something called a strain. And we call this delta L over L. So what is the change in distance across some distance that you are measuring? So remember, we had that ring that was oscillating. The distances were changing by some delta L. And so we were trying to measure this delta L, this change in distance across some measured distance. So the strain that LIGO is trying to detect from gravitational waves is 10 to the minus 21, which is really, really small. That's got a lot of zeros in it. And so this is comparable to saying that we are going to measure the distance to the nearest star, Proxima Centauri, to a precision of 0.04 centimeters. So Proxima Centauri is 4.2 light years away, and we're going to measure that to within about 0.4 millimeters. That is what LIGO is trying to do. And the old observatory head would tell us that, when LIGO first came online, he would go to other physics departments to tell people about this, and say, no, you've got too many zeros here, this isn't right. But this is actually what LIGO is trying to do. And so if we retake this equation, h delta L over L, if we instead put in the distance of LIGO's arms, which are 4 kilometers, so we put in 4 kilometers for L, that delta L, the amount that we're looking, is 10 to the minus 18 centimeters. So you're looking for a change in 10 to the minus 18 centimeters across a distance of 4 kilometers. And just as a comparison, this is an atomic scale. An atom itself is 10 to the minus 8 centimeters. A proton is about 10 to the minus 13 centimeters. So you're trying to get down to sizes that are smaller than a proton, which is pretty ridiculous. So these are really, really small things, really, really small distances. But what's actually producing this? Well, there are several methods that we can produce gravitational waves. One is a neutron star that is not perfectly symmetrical, and as it spins, it's going to be emitting gravitational waves at a single frequency, and so we can listen to it. So it's just a single tone, because it's a single frequency. And so we would expect gravitational waves from these neutron stars to be at just a single frequency. So for example, we saw in Mike's talk earlier that the Crab pulsar exploded in 1054. There's a spinning neutron star within that nebula, and it's predicted to be emitting gravitational waves at a frequency of 59 hertz, which is really unfortunate for us because our electrical system runs on 60 hertz, and so there's a lot of contamination that we just cannot get out. So that's why it's really awesome if we can move to a country that runs on 50 hertz, like Australia or Europe. The other big event that can create gravitational waves are compact binary coalescences. So if you have 2 neutron stars, which are the leftover remnants of supernovae, or if you have 2 black holes that are spiraling in towards each other and collide and coalesce, they will also produce gravitational waves, but this is going to sound a little different. Sorry? So that is called a chirp. And if you watch any gravitational wave video, there's always one of the scientists trying to produce that sound with their voice. It's pretty funny. So this, it's not just a single frequency, it actually sweeps across frequencies. So you're going down from 10 hertz up to about 200 to 300 hertz. And you might be thinking, wow, that sounds really awesome. I have to get that as my ringtone. Well, you're in luck because there are multiple ringtones available. Enchilada cool waves. There is gravitational wave chill out. But my favorite, I think, is black hole billiards. Yep. So you can go to this website, ligo.org/multimedia, and you can download your very own LIGO ringtone. So this is not something that we're making just to try to be clever as a PR stunt. While you cannot actually listen to gravitational waves, again, the detector does respond to gravitational waves within our hearing range. So LIGO is sensitive to gravitational waves from about 10 to like 500 hertz. That's about where it's most sensitive, and that's pretty close to what our auditory range is. So when I was there, when I was working on the interferometer, the output of the signal was actually plugged into speakers. So you could sit in the control room and you would just listen to the detector. And there were times where there were very characteristic glitches. So if you heard something like, you knew, oh, that's some glitch, I gotta go fix that. They haven't done that yet, and I'm hoping that they will because it's a really neat feature. But this is not, again, this is not something that we are just making up. You actually can listen to the signals. So it can be like Jodie Foster in Contact, where she's got her headphones on and she's listening to the Search for Aliens. I think she was looking at Vega, right? Yeah, I hope you've all seen that movie. So where is LIGO located? So LIGO is run by Caltech and MIT, and the original idea was to have observatories that are close to each campus, but politics got involved, and eventually they're about as far away from Caltech and MIT as possible in Washington State at Hanford, and then one in Livingston, Louisiana. And so again, these are mirror sites. The instrumentation is identical in both. The image here, this is aerial image of Hanford, aerial image of Livingston, Louisiana. Hanford's a desert, Louisiana is a swamp, so it's very different cultures, very different setting, but the instruments are the same. So how does LIGO actually do what it does? We need to start off with describing what an interferometer is, and more specifically, a basic Michelson interferometer. So we have a laser, we have a beam splitter, and then we have two mirrors. And down here, we're going to have a photodetector, something that's going to detect light. So a laser shines on the beam splitter. Half of the light is going to be split. It's going to bounce off and head up towards the mirror. The other half is going to pass through the beam splitter and hit this mirror here. The light that travels down this path is going to reflect off the mirror, and it's going to combine at the beam splitter, and we're going to view it at this photodiode, and we're going to get something called an interference pattern. And so that's this diagram here where you've got stripes of light and dark, light and dark. This is due to light's nature as a wave. Light is not just a particle, it is a wave. And when you combine waves, you can get interference patterns like this one. So LIGO takes this design, this interferometer design, and then it adds on extra mirrors, and this is called a Fabry-Perot cavity. So you've got additional mirrors which are right next to the beam splitter. In reality, they're about 10 feet away from the beam splitter, so they're pretty close. The distance, the 4 kilometers, is the distance from this mirror, these close by mirrors, all the way out to the end mirrors. That is 4 kilometers long. So you're shooting a laser 4 kilometers down this path, it's hitting a mirror, it's bouncing back, and it's going to resonate. It's going to bounce back in this cavity up here, and it's going to resonate. You're going to build up your signal. You're going to allow light to experience a gravitational wave for a longer period of time before it leaks back through this mirror and recombines to form your interference pattern. So remember at the beginning, we had this diagram of how a gravitational wave is going to stretch and shrink space. Well, if one end is stretching, the other is shrinking, this pattern is going to shift. So this pattern is going to shift back and forth at the frequency that the gravitational wave is moving those mirrors. And so if you put a photodiode at one of these fringes, at one of these patches of light, you can see it got bright, it got dark, it got bright, it got dark, as these mirrors move back and forth. And so we look for that, and we can say, well, this frequency that's moving at that matched what we would expect for a gravitational wave, therefore this is likely a real signal. So that's the basic idea of how this works. Of course, LIGO takes us 20 steps further, and there's a lot more mirrors and other stuff in these paths, but this is the general idea of how LIGO is trying to do what it's doing. And so this is the aerial view of LIGO Hanford. So within this little square right here, you can see it over there as well. So in this little building, you've got your beam splitter and you've got those 2 mirrors that are right next to that beam splitter. Then the light goes down this tube and it hits another mirror all the way at the end, bounces back, and then you've got this resonating light within those 4-kilometer tubes. If you look on the inside, this is what you see. There's a lot of stainless steel because this is all in a vacuum. It's very messy because when this was taken, they were doing an upgrade, and so everything was being taken out and things were getting put back in. But this is what the inside of LIGO looks like. So these are all vacuum chambers. This chamber over here, this is about 20 feet tall. These little ones over here, they're maybe 10 feet tall or so. And so they have all the mirrors, all the optics lie within these chambers. And these tubes, this is where the laser goes through as it's going all the way down 4 kilometers to that very last mirror. So the heart of LIGO is really going to be this vacuum system. If that vacuum system were compromised, the project would get shut down for years before they were able to bring everything back to normal. So the vacuum system is pumped down to 10 to the minus 9 torr, which is about 10 to the minus 12 atmospheres. So it's pretty empty. There's not very much stuff in there. And it's over 10,000 cubic meters. So this is one of the largest, if not the largest, vacuum systems in the world. The beam tube, this steel beam tube, is protected by a concrete barrier. This is during installation, so the beam tube is exposed. This concrete barrier is designed to protect the tube from things like bullets, because people do take pot shots at these buildings and at these tubes. They don't do anything to protect the people that are actually working in the building, because graduate students are more replaceable than a beam tube, right? But we have actually found bullet holes in the buildings where these things are, so there's a reason that you've got that concrete tube. Other good story is in Hanford. I don't know if you've heard of Hanford. It's been in the news lately because there's been some nuclear leaks out there. That's where they made all the plutonium in the 50s for the atomic bombs, and they didn't do a very good job of cleaning, so they just dumped everything into holes in the ground. And so they've got kind of like a paramilitary police force that protects that area from anyone, trying to steal nuclear weapons or whatever. And so they do maneuvers out in the desert, and they forgot where LIGO was one time, and so their Jeep went right into the beam tube. The person was fine, the beam tube was fine, the truck was destroyed, but it's a pretty good beam tube. They do a pretty good job of protecting this stuff. So to pump this down, to get this down to a vacuum, you want it to be very clean. If there's any kind of dirt in there, it can outgas, it can emit particles, and that will ruin your vacuum. So what they did is they basically hooked up this tube to electrodes, they ran a current through it, and that current made the tube really hot, so anything that was inside that tube kind of got shook off and vibrated off, and they hooked up a turbo pump to one end so they could suck all those particles out. But when this is exposed, when you're running current through this, you don't want anything to catch fire, so they put insulation all around the beam tube, 4 kilometers long. Actually, it's 8 kilometers for each interferometer because you've got 2 arms. And it turns out that mice really love insulation. They love to crawl in it and make it their home. And you're not going to remove 8 kilometers worth of insulation because why not? Why not just leave it there? Well, it also turns out that mice pee is corrosive to steel. And they were getting leaks at the Livingston site, and they were finally able to trace it back to the mice. So they had to undergo this huge project to remove all this insulation for both sites. It was pretty awful. The things they don't really tell you about in the press release about LIGO. So this is just kind of a snapshot of what you have to go through when you want to detect gravitational waves. You have to worry about mice pee. So the thing that I worked on was the laser system. So this is the whole laser right here. You've got 2 main systems. This little box is 35 watts. The big box is 250 watts. And all these other components on this table are designed to get that beam to be nice and perfect. It's going to be the right frequency, the right color, it's going to be the right power, and then it's going to go on into the vacuum, into the interferometer. So you need to not just have a really nice laser, but you have to have a really nice laser enclosure. So any kind of sound waves can vibrate the table, and that can change the power of the table, which can then mimic a gravitational wave. So they built this acoustic enclosure where it's got actually double walls, where the outside wall is not touching the ground, it's floating. So the idea is that a sound wave comes in, it's going to push on that outer wall, and it's not going to transmit into the inner wall and into the laser table. We also had this super clean room. It's a class 1000 clean room, which means you have, I think, 1,000 particles per cubic meter, which is a really small amount. And so we had to get this table cleaned, ready to go in this clean room. And we say we, I mean I had to do this, because my assistant lead, I don't think, really wanted to clean individually 11,000 tapped holes in this table. There were 11,000 tapped holes in that table. They each had to be individually cleaned. And then we had to, squirt some compressed air in there to get any kind of gunk that was out of it. So the reason I'm talking about this, again, is because it took a long time. It was a pain in the butt. And somebody also did not check their water fittings before they found a leak. This is a gigantic rust stain, so the rust actually got into the threads as well. So this was ugly, this was a mess. Check your water fittings. This is also the day I learned stainless steel is rust resistant, not rust proof. So we also have other things to worry about, like bugs, like actual bugs. So we had a bug climb onto one of the lasers and it got zapped. So nobody knew what happened. All anybody knew is that there wasn't any laser light getting into the interferometer, and eventually someone went inside and they actually saw this bug that was sitting on one of these mirrors, and its guts are everywhere. And I actually still have that mirror. So it's up here. If you want to take a look at it after the talk, you can still make out the guts that are on the mirror. The body has kind of fallen off somewhere in this container. But this mirror itself is about $500. We had to have some guy, the person who could fix this was in Livingston at the time, so he had to take a last-minute flight change out of Louisiana to Washington, which of course is like $1,500. So that bug, it's a very expensive bug, and hopefully with the new clean room we will avoid any more of these insects crawling on the optics. The most important thing in terms of detecting gravitational waves is being able to isolate your detector from the ground motion. So the ground is constantly shaking, and there are many reasons for that. There's wind, there's trucks, there's construction. So I mentioned that there's this nasty nuclear fuel that's out at Hanford. You can kind of make out some construction going on in the background. There's a vitrification plant that's being built. It's been like 10 years. It's always 10 years away from being completed. And that construction is picked up by the detector. And so you could actually tell when they would take their lunch break, because your sensitivity would suddenly jump up, and then they go back on and it drops back down. And then we would sometimes see some weird activity going on at like 7 p.m. out on this nuclear site. We weren't really sure if we should mention it or not, if this was some kind of thing that they didn't want to make public. So these are the kinds of things that you have to worry about when you're trying to detect gravitational waves. Because remember, if that mirror moves, it's going to produce a shift in that interference pattern. It's going to get brighter or darker, and that's going to mimic a gravitational wave. So you really want to isolate yourself from all these ground motions. At Louisiana, you have to worry about ocean waves because they're right next to the ocean. Since they're in a forest, a swamp, they've also got a lot of logging. They have a pipeline, an oil pipeline that runs right down the middle of the site. They also have alligators, which aren't really a noise source, but they're everywhere in Louisiana. And apparently one was actually getting a little too friendly with the staff because they kept feeding it, and so it would come up to them expecting food. So they had to call somebody out to take care of it, and then they got alligator tail later that day, so I guess it kind of worked out for them. So how do you protect yourself from this stuff? So originally, we had springs, lots and lots of springs. So this is an image of inside one of those vacuum chambers you saw earlier, and there are all these springs. The table would sit on top of these masses, and that would try to damp out any kind of ground motion. And again, there were so many of these, there was like hundreds of them, so people just went around and tossed them on people's desks. So I've got one right here. This was pulled from the vacuum, original, genuine, initial LIGO spring. You can feel it's pretty stiff because you've got a lot of weight to push down on this. And that was able to isolate from any ground motion. But it's not good enough. To get to the sensitivity that you really need to find gravitational waves, you need to have active isolation. So this will actually move the table to correct for any kind of ground motion that's coming in. So instead of passively just using springs to damp out the motion, you move the table itself. You also have to have really good suspension systems. So these mirrors are hanging on wires. Originally, they were hanging by metal wires. You can see right here, the entire cage was maybe like 3 feet tall, and they upgraded that to this gigantic monstrosity, which is like 5 feet tall. It's got so many different switches on it. I don't really know much about it because if you know something about the system, then that means you have to get in. I think the battery just died, so I'm just going to have to yell. Hello? Okay, I think we're okay now. So this is the upgraded. Okay, this is the upgraded LIGO suspension system. So what you have is there's actually 2 suspended systems. You got a reaction chain and a main chain, where the reaction chain just has masses to try to balance out the movement of the other main chain. You also don't want to push very hard on these mirrors. You want to keep them very steady, but you don't want to do it very hard, otherwise that's going to, again, create fake signals. So what they do is they have one gigantic mass sitting behind the mirror, and they coat it with gold. And if you run a current through the gold, it's going to create a force on the mirror that's right next to it, and so it's going to pull that mirror in, and that's going to damp out any kind of ground motion. So this really is what was able to create the very first gravitational wave signal, because you had this awesome suspension and this awesome seismic isolation. So on September 14th, they were able to detect the first gravitational wave signal ever found. Thanks. So this was found in both detectors. We knew about this within about 3 minutes of it occurring. It was picked up by automatic programs that look for these kind of events in the data. And so we knew right away that this had occurred, and it was a massive event. The energy that was released when these two black holes collided was equal to taking 3 suns and converting it to just pure energy. So that's like saying that the energy produced by this event is equivalent to the energy output of the sun over 3,000 times the lifetime of the universe. So this was a huge event, huge objects that collided, but still the amount that the mirrors actually moved is 10 to the minus 18 meters. Really, really tiny, really, really small movements by this gigantic event. So that's the kind of sensitivity you need to find even these massive events. And since then, there have been 2 more signals that were detected. This one was found just after Christmas in 2015. It was a less massive collision. So instead of you had 30 solar mass objects before, now you had about 19 and I think 10. You had less energy released. This was equivalent to taking 1 sun and converting it to pure energy. But because it's a smaller merger, it lasts a little bit longer. And by long, we mean like a second. The other one was about 0.5 seconds. So these are very quick events. And then just the other day, they announced the 3rd detection, which was found on January 4th, 2017. This was very similar to the very first event. You had massive objects, about 20 solar mass objects, that collided, created a signal that was very similar to the very first event. I wish that they would actually standardize the figures, because if you go across all these, they look very different. I don't know what's going on there. But basically, these were all huge events, black holes that were emerging. Originally, LIGO was hoping to detect neutron stars, which are less massive than black holes. But right now, the sensitivity isn't as good to detect neutron stars, which are smaller, so you can only find the more massive events of black holes. So what do we actually get out of this? Well, we heard earlier from Mike's talk that we know of black holes through X-ray studies, where we have companions to the black holes, and we can see them that way. And so we knew that there were black holes that were maybe 5, 10 times the mass of the sun. And we also knew that there were the supermassive black holes that were 1,000,000 times the mass of the sun. But now we actually have this intermediate stage of 20 to 30 solar mass black holes. And so we have to come up with good theories of how these occurred. We can explain the supermassive black holes pretty well, like we've got theories for that. We can explain these smaller mass black holes pretty well, we've got theories for that. But now you're in a position where you really have to explain how these events actually occur. And so that's going to be really a new, not entirely new, but a more looked at avenue of astronomy. And so I want to show you the conclusion. This is taken from the very first paper. And this is something you don't really see very often in research papers. So you have something so stark. You say here, these observations demonstrate the existence of binary stellar mass black hole systems. This is the first ever direct detection of gravitational waves and the first observation of a binary black hole merger. This is really the beginning of gravitational wave astronomy. Never before have you seen direct radiation, direct signals from a black hole until LIGO came along. So this is really the point where LIGO stopped being just a really engineering curiosity to an actual scientific observatory. And again, this is just the beginning. There's more to go. It's still going to be more sensitive. And if you look at this paper, there's like 800, 1,000 authors on this, because everybody that's involved in LIGO gets added onto as an author. I was not on it because you're left on the author list for a year after you leave. I think it was about 2 years after I left. So unfortunately, I did not get to be on that paper. But more importantly, I wrote my name underneath the laser table, so I think that's something. So there's Michael Rodruck was here, and in a few other spots as well, but I didn't take images of that. So what's next? Well, you're going to continue upgrading. There's more work to be done. You're going to get more science runs, not just with LIGO, but other detectors are going to come online in Europe, which, with Virgo, Kagra in Japan. They're building an identical LIGO site in India, which should be, I think, constructed